Hello everyone. Today I'm going to talk about the approximability of the eight-vertex model. This is a joint work with Jin Cai at University of Wisconsin-Madison, Tianyu Liu at Shanghai University of Finance and Economics, and Jin Yu at Georgia Tech. Let's look at the eight-vertex model. This model is defined on four regular graphs, although originally it was defined in statistical physics on the square lattice. The states of this model are even orientations of the edges, where the in degree of every vertex is even. So the out degree of every vertex is also even. There are 8 permitted types of local configurations around vertex, so there are 8 possible energy parameters, epsilon 1 to epsilon 8. The partition function is defined to be the sum of the weight on all even orientations, and the weight of each even orientation is in this exponential form. It's e to the minus beta times the sum of all the energies on vertices, where beta larger than 0 is the inverse temperature. We further assume the error reversal symmetry, or the so-called zero field assumption in physics, in which we assume if we flip all the arrows around the vertex, the energy parameter is not changed. So there are really 4 parameters instead of 8. And if you look at the partition function, you'll see that it's really a function of those exponential things. So we give them a name A, B, C, and D. So we can rewrite the partition function. The weight of each even orientation is the product of the weights on all the vertices. We know that the weight D is the weight for sink and source. In this talk, I will assume A, B, C, D to be non-negative. So in physics, the special case when D is equal to 0 is the 6-vertex model whose states are Eulerian orientations. The 6-vertex model was introduced by Linus Pauling in 1935 to describe the property of water ice and is one of the most studied models in statistical physics. The 8-vertex model was introduced by Sutherland and Fan Wu with the advantage that it's very expressive. It can not only express the 6-vertex model, but can also encode the diamond model and zero-field Ising model on the square lattice. Baxter in 1971 achieved a good understanding in the thermodynamic limit on the square lattice. In physics, it's called an exactly solved model. In terms of the exact computational complexity, this model was understood. On general 4 regular graphs, the partition function is sharply hard to compute unless in the 3 conditions. On planar 4 regular graphs, we know that the problem can be solved using the FKT algorithm when a squared plus b squared is equal to c squared plus d squared. So let's look at the approximate complexity of this model. In statistical mechanics setting, the square lattice 8-vertex model exhibit different macroscopic behavior under different parameters A, B, C, D due to the change in the inverse temperature beta. We record that A, B, C, D are functions of these in this exponential forms in beta and epsilons. So the ABCD will change according to the change in the temperature, inverse temperature beta. So there are 2 types of phases. One is called the disordered phase. It's representing the high temperature regime, and it's characterized by the 4 inequalities. Each of ABCD is less than or equal to the sum of the other 3. And there are another type of phases. They're called ordered phases. They're representing low temperature regimes. It's characterized by one of ABCD is dominant the sum of the other 3. Let's use the following notations. We use the script X to denote the whole disordered phase. In this picture, it's the red rectangle and everything inside. We use Y to denote the left oval. We use Z to denote the right oval. And we know that Y and Z are intersecting each other, and they do not contain each other. And they're both subregions of X. And some terms. In terms of approximation, we use the notion of FP-RUS. We use sharp PM to denote the problem of counting perfect matchings on general graphs. The approximate complexity of sharp PM is a central open problem. Whereas on bipartite graphs, it's already solved. With the n vertices, the number of perfect matchings is equal to the permanent of an n by n 0, 1 matrix. Jerome Sinclair and Jerome Sinclair-Vigoda are given F-PRS for estimating the permanent of an arbitrary n by n matrix with non-negative entries via Markov chain Monte Carlo. The only previous results for the eight-vertex model in terms of approximate complexity it was given by Greenberg and Randall. They proved torpid mixing of a specific Markov chain when D is large, or in other words, the temperature is low. This Markov chain flips the orientations of all four edges along a uniformly picked face at each step. This means that when sinks and sources have large weights, this particular chain cannot be used to approximately count or sample 8 vertex configurations on the square lattice according to the Gibbs measure. So recently we have two papers talking about the approximate complexity classification of the 8-vertex model on general four regular graphs. In this work, we proved two results. The first result is that there is an F-PRS for the 8-vertex model in the region Y intersecting Z. Second result is that the approximation of the partition function is NP-hard in all the ordered faces in the gray region. In an ACAL paper, we prove another two results. We prove that approximation is at least as hard as sharp PM if ABCD is outside of Y. So if it's outside this left oval, it's sharp PM hard. We also show that the problem can be reduced to sharp PM if ABCD is in Z, the right oval. And it is still open what's the approximate complexity of the region Y minus Z. In this paper, we also show that there's an F-PRS for the 8-vertex partition function in a subregion of Z minus Y. So the yellow region is sharp P complete in exact computation, is sharp PM equivalent in approximate computation on general four regular graphs, and admits an F-PRS in approximate computation on planar four regular graphs. To our best knowledge, they are the first identified problems having these three properties. Now let's look at the proof sketch of the F-PRS. We use counting via sampling via the method of Markov chain Monte Carlo. The specific chain we used is the so-called directed loop algorithm. The state space of this Markov chain are even orientations and near even orientations. By a near even orientation, we mean orientation of the edges such that for every vertex, it still obeys the even in, even out rule, but there are exactly two edges where if you view each edge as two half edges, the two half edges are disagreeing with each other. So you can see in the picture 2 and picture 3 on this slide, there are two edges with disagreeing half edges. And these two are called even or near even orientations. The transitions of this Markov chain are metropolis moves between neighboring states. One state can go to another state by creating, shifting, or merging of two defects on the edges. So we call such disagreeing two half edges and defects. So from the first picture to the second picture is creating a pair of defects. And from the second to the third, it's shifting this red defect to become this green defect. This chain was originally designed for the 6-vertex model in 1972 and used by a lot of scientists in physics to study the numerical properties of the 6-vertex model and 8-vertex model. So in order to count via sampling, we need to prove the rapid mixing of the Markov chain. So here's the technical lemma. We denote by z sub 0 to be the total weight of even orientations of the partition function, and z sub 2 to be the total weight of near even orientations. The lemma says if Z2 over Z0 is polynomially upper bounded, then the Markov chain is rapidly mixing in the region Z. This lemma was proved by a canonical path argument, which I'm not going to show here. We show that Z2 over Z0 is polynomially upper bounded in Y, and this gives the FPRS in Y intersecting Z. To prove this technical lemma, to prove Z2 over Z0 is polynomially upper bounded in Y, the following structural lemmas play crucial roles. A full reconstruction is a full regular graph having 4 external edges. A full reconstruction defines a constraint function. For a particular input orientation, the value is the sum of the weights of all valid internal configurations consistent with the input. So, and the function defines also satisfy the even in, even out rule and the arrow reversal symmetry for some A prime, B prime, C prime, D prime if every vertex inside satisfy even in, even out rule and the arrow reversal symmetry. And this whole thing, this full reconstruction can be viewed as a virtual vertex in the 8-vertex model. The first structural lemma says that the set of Fourier constraint functions lying in the disordered phase is closed under Fourier constructions. This reveals the structural difference between the two sides of the phase transition threshold. The second lemma says the set of Fourier constraint functions lying in the region Y is closed under Fourier constructions. This directly indicates that Z2 over Z0 is polynomially upper bounded. Later, I'll show why this is true. Now, in order to prove these two structural lemmas, we use the idea of decomposition of even orientations. We decompose each even orientation into annotated circuit partitions by pairing edges in all 3 possible ways. So for each even orientation and for a particular vertex, if we look at, for example, the top left configuration, it has weight A, and it has 2 incoming edges and 2 outgoing edges. So if we pair incoming edge with outgoing edge, we give a plus sign. If we pair incoming edge with incoming edge and outgoing edge with outgoing edge, we give it a minus sign. So you can see there are 2 ways of pairing them with plus signs and 1 way of pairing with a minus sign. For sinker and source with weight D, because you can never pair incoming edge with outgoing edge, so all 3 pairings give you a minus sign. So this way we decompose each even orientation into 3 to the number of vertices many annotated circuit partitions. It can become quite complicated. For example, in this simple picture with 2 vertices and 4 edges, there are 9 ways to decompose. This is a picture, the first example. And on the next slide, this is the second example. If you observe carefully, you can see that the only annotated circuit decomposition they share is the one in the middle. So the idea of decomposition also works for Fourier constructions. We can put weight W on local sign pairing set of vertices, just like we can put weights on one of the 8, each of the 8 local configurations. So we can also define the weight of an annotated circuit partition to be the product of weights on vertices. And we also define the weight capital W of global sign pairings for the Fourier construction as a virtual vertex. For example, for capital W on this kind of pairing with a plus sign, we define it to be the sum of the weights of all annotated circuit partitions where E1 and E2 are paired together, E3, E4 paired together with a plus sign. Now let's look at how do we prove the closure properties. For the first closure property, for the disordered phase X, we decompose with weights under weighted decomposition. Constraint function being in X at every vertex means that there exists a non-negative W of signed pairings at every vertex, which means the weight of annotated circuit partitions of the Fourier construction are non-negative because the weight of annotated circuit partition are really coming from the product of signed pairings. So this means that the induced weight function capital W of the global signed pairings of the Fourier constructions are non-negative because they are sum of the weights of annotated circuit partitions. This in turn means that the constraint functions of the Fourier construction itself must be in the disordered phase X. For the second closure property, we still use the same weighted decomposition. This time, constraint function being y at every vertex means that at every vertex, sorry for the typo, at every vertex, the weight of a pairing with a plus sign is not less than the weight of exactly the same pairing, but with a minus sign. So with quite complicated and technical analysis, we can show that induced weight function capital W of the global signed pairings also has this property, which means constraint function of the Fourier construction must also lie in Y. So now we have the second closure property. How do we prove Z2 over Z0 is polynomially upper bounded? We show it by showing that Z2 sup E prime sub 2 over Z0 is polynomially upper bounded for any E and E prime. And this funny notation E sup E prime sub 2 means the sum of the weights of near even orientations where the defects are on exactly E and E prime. So for a particular pair of edges, E and E prime, we can view it as a Fourier construction by cutting it open at the middle of two edges. And if we observe carefully, we can see that the total weights of configurations with defects on E and E prime are equal to the sum of A prime plus D prime with a factor of 2, and A prime, D prime are coming from the constraint function A prime, B prime, C prime, D prime of the Fourier construction. And similarly, we can show that the total weights of configurations without defects are equal to 2B prime plus C prime. And because we know that A prime plus D prime is always less than or equal to B prime plus C prime in the region Y, we know that Z2 sub E prime over Z sub 0 is always upper bounded by 1. This is how we proved the Z2 over Z sub 0 is polynomially upper bounded. So finally, let's look at the proof sketch of the NP-hardness. We want to reduce the NP-hard problem computing the max cut on 3 regular graphs to approximate counting the partition function of the eight-vertex model for A larger than B plus C plus D, for an example. And the proof for all other 3 cases are similar. We need 3 types of gadgets in this reduction. The first type of gadget is the Fourier construction that amplifies the ratio between A and BCD. The second is a four-way connection implementing a single edge in 3 max cut. And the final one is a locking device implementing a vertex of degree 3 in 3 max cut. In the next 3 slides, I will show each of them. First, an amplifier. Starting with A sub 0, B sub 0, C sub 0, D sub 0 equal to A, B, C, D, after repetitively applying this amplifier k times, we have the ratio of AK over the sum of BK, CK, DK is no less than omega of beta to the 2 to the k for some beta larger than 1. This means that the ratio of AK over the sum of the other 3 are growing exponentially fast using polynomially many vertices. We can assume that we have A tilde, B tilde, C tilde, and D tilde with A tilde larger than the other three, and the other three are roughly 0 in the approximation sense. Now, how do we encode a single edge in the max cut? We use the following gadget. So we put a tilde, b tilde, c tilde, d tilde, this constraint function at x and y, and abcd at m and m prime. So we assume, we imagine this x and y are vertices in the max cut problem, and m prime denotes the connection between a single edge between x and y. So because we're putting this a tilde, b tilde, c tilde, d tilde on x and y, they are in one of two possible configurations. This is in perfect correspondence with the idea that in a max cut problem, each vertex is in a plus state or a minus state. And because A is larger than D, and this M and M prime can only be in weights of weight A or of weight D, we can use this gadget to make sure that it favors this plus minus or minus plus on the X and Y over plus plus or minus minus. So this only implement a single edge in the max cut problem using a four-way connection. We need to implement a degree 3 vertex with 3 four-way connections. We use the following gadgets, and the 3 four-way connections are I prime, JJ prime, and KK prime. We want to make sure that as a whole, to represent a degree 3 vertex, this gadget is always in one of the two possible states. So we can use it to represent a plus state and a minus state in the mixed cut problem. Final comment is that all three types of gadgets are bipartite, which means approximating the 8-vertex partition function for A larger than B plus C plus D is NP-hard, even on bipartite graphs. And this is all. Thank you for your attention.